So this is the outline, the electric. We'll talk about the electric potential, equipotential surface, and the electric field. And similar to the previous chapter, we will mention how to calculate the potential due to different geometric structure. Yeah. So here comes the definition of the electric potential. So we usually denote it as V at the point P. So in the electric field of a charged object is this one. The V is this is the omega. W infinity is the work that will be done by the electrostatic force on a positive test charge, where it was from infinite distance to P. So which means that the potential energy at infinite far away is 0, and then we need to do some work to bring it to any point P. And actually, the definition is like minus W infinity over this Q0, the positive test charge. So this minus work done is actually the potential energy at that point P. So U is the electric potential energy that would be stored in the test charge object system. So which means that in this figure, you can imagine we have. So first of all, you ignore this test charge first, and then we have a charge rod with positive charge. So it will generate an E field in the space, something like this. And actually, at point P, if you place, if you move a charge from infinite far away, this charge move from infinite far away to here, you need the work done, W infinity. So, and actually, as long as this is positive, this is also positive. So they will repel each other, which means that you really need to spend some effort to put the charge there. So in this case, this is how the electric potential defined. So the electric potential is defined independent. Actually, this whole term will be independent to the Q0 itself. So here, using 24.2, we multiply Q0 on both sides, so we will have U equals QV, U equals QV. So U is the electric potential energy. And in this case, we have some variables. So here, first we define the potential difference, delta V. Actually, the electric potential is a scalar, different from the electric field. Electric field is a vector, so that it has different components. However, V is only a scalar because energy is a scalar. So this is very important. So actually, we can divide the potential difference between 2 points is just by simply subtracting the electric potential of them. So we have a VF minus VI, which is delta V, and then if we multiply by Q, then we know that the potential change, the potential energy change is Q times the delta V. And the work done is minus delta U. The work done is minus delta U. And actually, this is the conservation of energy, which means that suppose without any loss, which means that the mechanical conservation of mechanical energy. Conservation of mechanical energy. Mechanical energy is like K plus U. K is the kinetic energy, U is the potential energy. So K1 plus K1 plus U1 equals K2 plus U2. So which means that if we just put let me see. If you put K1 to the right side, U2 to the left side. So on the left side, we will have minus delta U equals delta K. So this is how this look like, because minus Q delta V is actually minus delta U. So delta K is minus delta U. And actually delta K is minus delta U plus W applied, which means that for the third case, conservation energy means if you don't apply any work on it and without any loss, then we have conservation of mechanical energy. Here, if we apply some work on the charged particle, then the total energy, the total mechanical energy will change due to this work done. So here is an sample problem. So electrons are continually being knocked out of air molecule in the atmosphere by the cosmic wave particle. Coming from the space. So air molecule 就是那些空气的分子cosmic wave 是那些宇宙的粒子一般是一些高能量的粒子。So usually high energy particles coming in from the space. So you knock out the electron from the air molecules. Once release, each electron experience an electrostatic force due to the electric field either is produced in the atmosphere by charged particle already on Earth. So we assume that we have the E field pointing downward, which is 150 Newton per Coulomb, and is directly downward. So what is the delta change? The change delta U in the electric potential energy of a released electron when the electrostatic force causes it to move vertically upward through D equals 520 meters. So it actually moved upward. So there's a force acting on it to make it move upward. Because yeah. So what is the potential change? Potential change. So actually this would be very simple, because W is nothing but F dot D. So F is QE dot D. So actually Q is an electron, and E has its opposite direction. with the D, which means that it will become minus Q ED. So we substitute all the numbers in it. Q is the electron, so it is minus 1.6 times 10 to minus 19 times 150 times D is 520 meter. So it would be 1.2 times 10 to minus 14 joule. And delta U, what we need to find is actually minus W. So it would be minus 1.2 times 10 to minus 14 joule. So you can simply imagine, because E is pointing downward, and then E is a negative charge, so even without applying any force, it will try to move upward. So actually delta V, we also want to find what is the potential change. So delta V is delta U over Q. So it is minus 1.2 times 10 to minus 14 over minus 1.6 times 10 to minus 19. So it would be 4.5 times 10 to the 4th volts, or 45 kilovolts. 45,000伏，45,000。So any questions? So next we talk about the equipotential surface. So this is a similar concept like the electric field line, but here is a bit different. So the adjacent point is like the equal height point in the map, something like that. So the adjacent point, for the adjacent point that have a same electric potential, form the equipotential surface. Equipotential surface, which means that suppose this 1, 2, 3, 4 are 4 equipotential surface, which means that for this one, we all the potential on this surface is also V1. It's also V1. And for this one, all the potential are V2 and so on. Actually, it is also an imaginary surface. It does not really exist. Even in this space, you can actually calculate the equipotential surface. So it's not really a surface there you can see. So the work done by electric field on a charged particle, as the particle moves from one end to another of path 1 is 0. Path 1 is 0. So here you can see we have path 1 here. So the starting point and the end point is still on the V1. So the potential change, the electric potential change for path 1 is 0. And for path 2, and actually you know that for path 1, the whole path is on the V1. And for path 2, the starting point and the end point are also on V3, but the path along is not on the exactly on V3 surface. However, the potential change from the starting point to the end point is still zero. It's still zero, which means that it only depends on the starting point and the end point. The path itself is not really, it's not related. It's not related to the potential change. Of course, in between, the potential may change. But if you just consider the starting point and the end point, the potential between those 2 points, then it doesn't really matter the path. You may go like this, or go like that, or go like this. So the potential change comparing the end point and the starting point is still zero for this path 2. And for path 3 and path 4, the potential change is not zero and the work done is not zero because, of course, we assume V1 is not equal to V2 is not equal to V3 is not equal to V4. They are mutually distinct. So path 3 is moving from V1 to V2. So the potential change in U3 is Q V2 minus V1, something like this. And for path 4, it also moved from V1 to V2, but it go over and go back. But actually, these 2 paths has the same work done because it only depends on the starting point and the end point, whether it's on the same equipotential surface, or maybe not, but it only depends on V2 minus V1, V2 minus V1. So they could be the same. So mention that path 3 and 4 connect the same pair of equipotential surfaces. So which means that the work done for path 3 and path 4 is the same. So at the same value, it's not equal to 0. So any questions? Okay, so so here let's write this mathematically. So previously we in this page we only talk about the quantitatively. So qualitatively we need to write it in a mathematical way. Actually, as you can see here, so this is the point I, this is the point F. So I is the initial point, and the F is the final point. So the electric potential difference between 2 points, I and F, is VF minus VI. So it will be a line integral E dot ds integrate from I to F. So I'm not sure whether you have learned the line integral in mathematical class yet, but actually it is something like the 1D, similar to the 1D integration. Similar to the 1D integration. When you learn the 1D integration, it is something like integrate for f of x dx from a to b, something like this. Here, we talk about we integrate over a path, which means that within the space you can see the E. So all of these are the E field lines. So for example, for these points, we have we have the E like this. We have the E field like this. And then it should dot with the DS. DS is the tangent line. DS is the tangent direction. And of course, DS is very short, infinitely short. So we calculate E dot DS at this point. So we have E dot DS at this point, and then we calculate all the points from I to F, and then we add all of them together. So this is the definition of the line integral. And also we still have a negative sign in the front. So this is the definition for the potential difference. So the potential difference is the line integral of the E field over the path, but with a negative sign. So take over any path connecting the points. So if the integration is difficult along any particular path, we can choose a different path along. Choose a different path along which integration might be easier. Maybe you choose a straight line, maybe sometimes you choose a circle path or whatever. Or an arc within a circle, maybe sometimes it will be easier. So if we choose Vi equals 0, which means that the initial point is at infinitely far away, for the potential at particular point, V would be like this, because we just let Vi equals 0 at 24.18. So for the simplest case, for 24.19 or 24.18, this is what you should supposed to learn in high school physics. So in a uniform field of magnitude E, the change in potential for a higher potential surface to a lower one, separated by distance delta x, is delta V equals minus delta E times delta x, minus E times delta x. Yeah, so yeah. So which means that here we assume that E has the same direction, which means that it is like the E field. Sorry. The E field may be pointing from this way to that way, and then you maybe we have a uniform E field pointing to the right side, maybe something like this. And then we move this point maybe from here. This is the initial point. This is the final point, and then you move this way, so that this is a straight path, which means that delta ds always point to the right side, or always point to the right side, which means that E is uniform. E dot ds is always a constant. E will be like E ds, and then you will integrate a constant. So it only depends on, it will something like E times delta x. You integrate a constant. It's something like you integrate a constant from maybe 0 to 3. So it is something like 3 times 4, which is 12. So this is similar to that case. When you calculate a line integral and the path is a straight line, it reduced to a 1D integration. So this is what you should have learned in high school. And And similar to previously, when we use the Gaussian Gauss law, E dot dA, and you consider the E field is uniform over the Gaussian surface, it will something like E dot A, and sometimes it's spherical, so A will maybe 4 pi r squared, something like that. And here it is similar to that case. So here is an sample problem. Any question up till now for this, for the equipotential surface and the electric field? And actually, one thing I forgot to mention is, yeah, for the voltage or actually the electric potential V, the SI unit is V. I'm not sure it should be not mentioned here. So the SI unit is V, volt. Sometimes I will call the electric potential as the voltage. Voltage is something like in the circuit theory, when you consider the distributed circuit element, then we will use a voltage rather than electric potential. But they refer to the same thing. But yeah, actually, electric potential is a more general idea than the voltage. But actually, the SI unit for V is actually V, which is the short form of volt. So when you learn the E field in chapter 22, you know that the E has a SI unit of N over C. Here we can also have V over M. Both are correct. Because this is V, this is the unit for E, this is meter. So V over M is the SI unit for the E field. So both are correct. So here's a sample problem. So 2 points I and F. Here is I, this is F, in a uniform electric field pointing downward. So the point lies on the same electric field line not shown and are separated by distance d. So d. So find the potential difference Vf minus Vi by moving a positive charge Q0 from I to F along the path shown, which is parallel to the field direction. So this is easy. Vf minus Vi is minus integration of E dot ds from I to F. So E and D. So D from I to F, which means that ds pointing downward. So ds and E are points to the same direction, which means that we have actually E dot E times D. So this is very, very easy. Any questions? Okay, so for part B, so now we do not go strictly from I to F. We go to C first. So the C is actually, this path is actually perpendicular to the E field. And then move for D. So this is actually D. And then go 45-degree angle with the E field and then go to F. So now found the potential difference Vf minus Vi by moving the positive test charge along the path ICF. Yeah. So first, Vc minus Vi. Actually, if you have learned this concept, if you have understand this concept, you know that even you go along this path or that path, it should be the same. But actually, it lets you have some feeling. So we have the integration from I to C E dot ds. So here we have ds in this direction and E is pointing downward. ds point to the right side, E point to downward. So they are perpendicular to each other, which means that this integration should be zero, because E and ds are perpendicular. So next, we consider from Vf to Vc to Vf minus Vc, which means the potential change from point C to point F. So it should be minus integration from C to F E dot ds. So here ds point to the bottom left and E point to the bottom. Yeah. So which means that E dot ds is something like E ds cosine 45 degree, because yeah, so actually for the inner product, it should be the magnitude of this one multiplied by magnitude of this one multiplied by the cosine of the angle between them. So EDS cosine 45 degree. And actually, as you can see here, this triangle, this side equals this side. So this is D, this is D. So this path is square root of 2D. So which means that we have a E dot ds from C to F, which is E times square root of 2D, and then cosine 45 degree is square root of 2 over 2. So actually they cancel. So it would be minus ED. So Vf minus Vi is calculated by adding these two together, which is 0 plus minus ED, which is minus ED as expected. Any questions? Okay, so next we talk about the potential due to the charged particle. So it is something similar to the E field due to a charged particle, but now we talk about the potential, electric potential due to a charged particle. So now we assume in the space we have this charge Q. It can be positive or negative, but it only changed by the sign. So we just assume this is a positive charge here, and then it is evaluated by so we have a positive test charge Q0 here. So the E field generated by the bottom charge will be pointing upward at this point. And so we assume that this charge will move from this point to infinite far away. infinite far away, which means that VF is 0 at infinite far away. VI is we hope to find the V at this point. We hope to find the V at this point. So we make this setting. So this is I, F is at infinite far away. And the E field is pointing from the I to F, pointing from I to F. So we have VF minus VI equals, this one is the definition. And we know that E pointing upward, DS also pointing upward. So E dot DS is nothing but ED R. It's just changed the variable name, so but it doesn't really matter. So you can imagine this is the original point, and the R axis is pointing this side, pointing upward. So this is R, this is R. Or R as, or it consider the point. It actually consider the V at this point P, which has a distance capital R from the charge. So it's actually integrating from capital R to infinity, because the path is from capital R to infinity. This one is just a middle point. It's just a middle point. So this is R. So this is R. Small r. So we integrating EDR from capital R to infinity, and then take the minus sign, which is VF minus VI. And also we have VF equals 0, VI equals V. So the left side will be 0 minus V. And then E is not a constant, so that we cannot just write E times the distance. And actually the distance is infinitely long, because infinite minus capital R is still infinite. So this is not the case. And actually we need to really use E equals KQ over R squared. KQ over R squared. So we substitute this into this expression, so that we will have a Q over 4 pi epsilon naught, and then dr over R squared. So Q and 4 pi epsilon naught are constant, so that we just bracket out, and then inside the integration, so it is dr. So we just keep R 1 over R squared inside. So for this integration, it is minus 1 over R. The minus 1 over R, so that it cancels this minus sign, so that it becomes Q over 4 pi epsilon naught times 1 over R. And then we evaluate at infinity and capital R and subtract them. So finally, subtracting infinity into this expression will be 0. And then finally, it would become minus Q 4 pi epsilon naught times 1 over capital R. And then here we also have a minus sign, so that these two minus sign cancel. So finally, we have this expression. And it just replace capital R by small r. So, but it is just a variable defining that the distance between the point you consider and the original charge particle. So V is 1 over 4 pi epsilon naught times Q over R. So this one. So we come up with some similar expression, like F is KQ1Q2 over R squared. And then E is KQ over R squared. So now we only have Q over R. And then some page later, you will see U is K Q1 Q2 over R. So 4 similar expression. So actually here we it tells you that similar to the previous case, if we have a multiple charged particle, a collection of charged particles, then the way to calculate the potential at a point, then you can calculate the electric potential due to each charged particle one by one, and then you add them together. But it is easier. But it is easier than the calculating the electrostatic force or the electric field, because they are vectors. But actually, voltage or potential, electric potential is just a scalar. So that you adding them together is much easier. It's much easier. Thus, the potential is the algebraic sum of the individual potential with no consideration of direction, so that you don't really need to decompose it in different direction and then add along that direction to form the vector. So a positive charged particle produces a positive electric potential. A negative charged particle produces a negative electric potential. So here's a checkpoint. So the figure shows three arrangement of the two photons. Rank the arrangement according to the net electric potential produced at point P by the proton rated first. So actually, so this is proton. All the red dot are proton. So we want to evaluate the potential at point P. So it asks you which one. It asks you to rank them. Which one is the largest? Which one is the smaller?哪一个最大 ？A、B、C。哪一个最大？觉得 A 的举手，觉得 B 的举手，觉得 C 的举手，全部都放弃。觉得 C， 觉得 C 吗 ？OK， 那其他大部分都没举手，所以是什么？所以答案是全部都一样啊 ，the same。So because it's only consider the algebraic sum, so all of them are proton. So this one should be the same as this one, should be the same as this one, and this one should be the same as this one, should be the same as this one. You don't need to consider the E field. So actually, when you only consider the V, they just add them together and they should be the same. But when you consider the E field, it will be like it pointing to this side. For this one, you will point to this side. So this one, it will point to this side. So when you consider the magnitude of the E field, A will be larger than B, will be larger than C. But when you consider the electric potential, actually all the three cases are the same. LG baric sum of the V1 plus V2. So V1 is nothing but K times Q over D, and then this one is K times Q over D square, right? D square D. So this is Q over capital D. So add them together. All of them are this value.